All right. Those of you who braved the elements right before spring break. We'll go through a little bit of new material today. Kind of revisit something different and kind of revisit what we talked about on Wednesday. So the Connect Cell assignment, due dates are after spring break, but like I mentioned, especially the first, I think, on this on the Connect assignment, I think you can get all the way through like question 15 or 16 after what we've done this week. So you should be able to get the majority of that or work on the majority of that. The Excel, the first question we've already covered. The second two will be what we do that first week after spring break. Okay. That being said, let's jump into things here today. So go back a little bit. Monday, we talked a little bit about bias that can exist. We talked about we want to get a sample that looks as much like our population as possible, right? And so what can go wrong? Like we tried to account for all these things. We talked about stratified, cluster random sampling. But what else can go wrong, right? So kind of the motivating example for this is going to be the 1936 presidential election. Al Bland was the other candidate who lost to Roosevelt, FDR. We know this now. But at the time, there was this kind of literary digest poll. My grandma used to like the magazine or something. And they sent out 10 million survey cards. They got 2.5 million back and figured, okay, we could make a prediction about the election based off of these surveys. Right? So the survey cards predicted that there was going to be a huge landslide, 57% of the popular vote, huge amount of the electoral vote. But it predicted that Al Bland was going to win. Now we know what actually happened. Well, I think my battery must be dead. Was that Roosevelt won, but not only did he win, he won the landslide. So not only did they get the prediction wrong, they got it really wrong, right? So what ended up happening is that ends up being a really good historical example where we can look at two different types of bias. And we can think about more, but two main ones, right? So this is just stupid, like how did they do the wrong equations, right? What were they doing wrong? Well, maybe they mailed more cards to Republicans. So then when they got them back, it was more likely that they were going to predict the Republican candidate was going to win, right? But why would they have mailed it out to more Republicans? That wouldn't have been something you would think that they would have tried to do. Maybe it was just that Republicans were more likely to respond. For whatever reason, maybe all these surveys, if I sent 5 million to Republicans, 5 million Democrats, if I got 0 back from Democrats and 2.5 million back from Republicans, well, my sample is going to be skewed, right? So these are really kind of two examples of what we're thinking about is the selection and then the non-response bias. So a selection bias is if we're over-selecting from a certain group that we know is going to have a certain response, right? Or when I say a certain response, it doesn't have to be a survey. You know, if I was interested in something like income, maybe it's if I only send it to people who have country club memberships, I know I'm going to be getting a much higher income level than if I just randomly selected people. Non-response bias would be, for whatever reason, there's just one group that doesn't respond to whatever the survey method is, doesn't respond or doesn't get collected in the data. And so we want to try to eliminate both of these. So we'll look at a couple different examples, but we'll think specifically about this presidential election first. So the way that they sent out these survey cards was they cross-referenced names that were in telephone book and had car registration. So in order for them to be in this list of people they were sending these survey cards out to, those people had to have a telephone number and they also had to have kind of a car registered. In 1936, what do you think the kind of people who have both of these are? Yeah, wealthy, right? So I'm going to be over-selecting wealthy individuals, right? When I look at the correlation between income and party choice, tends to be higher income is more likely to be a Republican or, identify as Republican. And so sure enough, if we look at this, right? Those who owned a car and telephone, what this study did was it tracked people down who voted in the 1936 election and looked and said, okay, who did you actually vote for, right? These survey cards were like from 1936. They then went back out and got like 2000 or something current data, right? Where it was people said, how did they actually vote and what was their car and telephone ownership at the time of the election? And what they found was, sure enough, the literary digest poll was correct, right? They were a little bit off. They predicted 57%, but of those who owned a car and telephone, about 53% of them did end up actually voting for Landon, right? So the only reason they got it wrong is because they were over-selecting, right? And here they weren't just over-selecting, they were only selecting people who had cars and telephones tend to be more likely to have higher income, tend to be more likely to be Republican. If they would have just done one thing, which is not cross-reference these lists, so there's two issues, kind of the car issue, right? 1936, not only do most people not own a car unless you're wealthy, right? It might be more likely that people who own a car don't live in a city where there's public transportation, right? Maybe I'm over-selecting kind of rural areas as well. Also, telephone only. You can kind of see there. If I, think about who had telephone lines, you go back out to the country. It's not as likely that we're going to see people kind of having their own telephone number at the time, their shared lines, things like that. So they just wouldn't have cross-referenced it, and they only use anyone who showed up in either list. Someone who only had a car or only had a telephone. Right? Notice for those people, about 60% actually ended up voting for FDR. But those people weren't in their sample, right? The only people that were in their sample, people who owned a car and telephone. And in fact, if you go to people who had neither, because they're probably like very poor rural people, as high as 73%, right? So it's kind of a nice example to highlight this selection bias. I don't want my mechanism for randomly sampling people to be related to my variable of interest at all, right? If I'm interested in who someone's going to vote for, I don't want to be over-selecting from certain income groups, right? Because I know there's some type of a correlation between income and political party affiliation. So what about the other bias? So we could have non-response bias. I gave an extreme example earlier where no Democrats send this back, even if they did send it to like 5 million Republicans, 5 million Democrats, and they get 0 back from Democrats, 2.5 million back from Republicans. That would be the idea. For some reason, Republicans were just more likely to respond to this survey. So they did the same kind of thing, went back, looked at these different groups. Now, these were the only people in the actual survey who had a car and telephone. And what you see here is about 35% of them returned this straw poll. So they sent out another poll, and that wasn't this specific survey, to see just kind of what was the response rate of people who actually voted for Landon or actually voted for Roosevelt, and their likelihood of returning this additional kind of straw poll, like in whatever year 2000. And notice it doesn't really actually matter here. If they only selected people in the car and telephone, but even if they would have done car, telephone only, or neither, every single time, for whatever reason, people who actually voted for Landon were just more likely to respond to some kind of a ballot or a survey or some kind of a poll, right? So even if they wouldn't have just selected on cars and telephones, this non-response bias was kind of baked in there as well, right? So we had this non-response bias, which were registered Republicans or people who ended up voting for Landon were just more likely to respond to the survey. And we had this selection bias that we were over-selecting kind of wealthier individuals here owning both a car and telephone. So this is kind of a good example. We can kind of go back and look at those two biases that existed. We'll go through some more. I'll kind of point out how we can identify these in other situations. And then we have some other bias that can exist, which is that when we're collecting data, especially if it's survey data, people might lie to you, right? Either maliciously or non-maliciously. So, perhaps it's not that they're, you ask them what their income is and they're say, I don't know, $60,000. In reality, they make $57,345. They're technically lying to you. They're technically giving you data that's not accurate. Now, they're not maliciously trying to lie to you. They're just, out of nature, rounding up to, the next 10,000, right? Or maybe they don't remember exactly how much they made, so they tell you, 58,000, or they misremember exactly what their income was in the prior year. So a lot of non-malicious lying, and sometimes it's as simple as whatever you're asking or however you're collecting the data, the question isn't clear to that person, right? So there's a whole bunch of evidence out there now. I saw this one. I should try to find it for when we get that for spring break, because we'll use some other examples too when we talk about bias. But it was a Fox News poll, and it was like they asked 2 questions, and it was about at the time how people thought President Trump was doing running the country or something like that. And the one they preceded it with, in light of these negative things, how do you feel that he's doing? And then the other one, I think it was they listed some positive things and said, how do you feel? And the difference in the response rate was something like 10 to 15% difference, right? In terms of how people view they were doing, just by setting up the question with some positive or negative statements could influence how people then kind of responded, right? So how's the question phrased? Is it subjective? Is everybody understanding the question the same exact way? That may kind of lead into this non-malicious lie, right? And then malicious lying, right? That's just, if I'm collecting data on drug use for, go figure, the drug use survey data is way below, like if we try to figure out that, get an idea about the sales data of drugs, right? So it's, people sometimes will maliciously lie to you too, because they don't want you to know what the actual information is. So usually, I wasn't using iClickers today, so usually I would do iClickers and we kind of take a look at this. But I think you can get the idea even if we don't. So let's say I was to kind of poll all of you. I was using this like as an iClicker question. I said, how would you rate your health from 1 to 4? Right? So how would you rate your health? So everybody, you would kind of look at this. Okay, what do I feel today? Respond. We then kind of take a look at it. If I looked at the average kind of self-reported health rating for this class, what's probably true about that sample relative to the population? Hopefully. Think of the selection bias that exists for you guys relative to the population as a whole. You're quite a bit younger on average, right? I would hope you have better health than the entire population. That includes 80 and 90-year-olds, right? So we know that automatically I have a selection bias. I'm over-selecting from a younger age group, right? So that's my selection bias. Now, if I had set this up as an iClicker question, what bias did I hopefully shut down? Well, unless you don't want to get the points, I would hopefully shut down the non-response bias, right? Everybody would be responding because there's an incentive tied to it, right? So this is a good kind of point. Like if I was just kind of tying an incentive to answer this question, it's likely I get everybody to respond. So if I'm worried about survey data and not getting enough people to respond, what might I do? Well, this is like the emails you get here, enter, fill out this survey and enter a 20 gift card, or fill out, I get these emails all the time about like, fill out this survey and you get a chance to win this. I mean, it's a small incentive, right? It's not going to incentivize everybody, but if you can tie an incentive, right, to responding to your survey, you can essentially shut down that non-response bias, right? What are some other things that could happen here? Most people think they're in worse health than they actually are. So if you look at self-reported health versus like actual medically calibrated measures of health, people always think they're more unhealthy than they are. It also could be that you misread the question, right? If I said, how do you feel, rank yourself from 1 to 4? Maybe you think, oh, I feel like a 1, like 1 is best, or maybe I feel like a 4 is the highest number, that should be the best. But if I read the question carefully, 4 was actually the lowest, right? So maybe I get people kind of exactly, reporting the opposite of how they feel just based off of misunderstanding that question. Oh, another one good to point out here. I gave you 4 options, and something like this, I made it discrete. What if you feel like a 1.5? Right? What if you're somewhere in between a 1 and a 2? Well, you have to tell me either 1 or 2, and so by making it discrete, you're not kind of maliciously lying to me, but you're having to round how you actually feel about your health or whatever the options are, right? So we usually don't like to kind of have these limited options. We like to leave it kind of open-ended, right? So we talked about selection, non-response bias. People might non-maliciously lie. Maybe if, people thought I was going to look at the data, maybe they maliciously inflate their health. So I don't think that they're, not doing well. But then another example, we can think about these same types of bias that exist. So if I were to kind of poll you guys, how many alcohol drinks do you have an average per week? I give you these 4 categories. And then, look at the responses. What's a selection bias that I probably have built in? You're my sample. What do you think is probably true about your drinking behaviors relative to the population as a whole? Probably quite a bit higher, right? I've over-selected not only have I selected under lower age individuals, but I've over-selected college underage individuals, right? And so I automatically know that I'm probably going to get an inflated, sample mean relative to what the true population mean actually is, right? Once again, if I'd use this for an iClicker question, hopefully I shut down that non-response bias. But this is like anything, even when I'm doing regular survey data. If I know that this data is being recorded, and for whatever reason, if you're not 21, you have any worries about me looking at the data and seeing that you're responding that you're drinking more than 12 drinks a week, well, maybe you don't even just respond. You're like, yeah, it's not worth the iClicker points. I'm not gonna like kind of go there, right? But I mean, hopefully, I'm not malicious. I would never do something like that. But the idea is, I can try to shut down these non-response bias with incentives, but sometimes there's still going to exist incentives for someone not to respond that you can't shut down, right? So anytime you look at drug use data, right? in the rare case that when I report my drug use that somehow someone sees it and I get, arrested or whatever, well, I may not just respond to that survey. I'm not going to take the chance, right? So we still have this non-response bias built in, even if there are incentives that exist. So that we've got kind of that selection, we've got our non-response bias. I could also have had people maliciously lying. If they're not 21 and they think I'm going to look at this data or give it to anyone, maybe they respond with a 0, right? Or if I'm looking at drug use data, always you see a lot of people just respond with 0, even if we, they actually are using the drug. So we kind of talked about, I didn't tell this one, but you could have people like also just got one guy at the party who wants to tell you how much they drink, right? So you might have people just like making up the data or lying that's just looking at survey data. So in general, these biases that exist in our data, it's really prevalent in survey data. So we want to try to get different recordings. Like if I'm looking at income, I don't want to get self-reported income. I probably want to try to get like data from the IRS or Bureau of Labor Statistics or something like that. Right? I don't want to rely on people's responses, because if I'm relying on survey data or people's responses, a lot of times it's hard to remove these biases, right? People are not going to give you accurate information. And so you want to try to find a way that, or try to find a method that has recorded data that is not subjective as much as we possibly can. Okay. So I thought this is kind of interesting. Recent example, I had this paper, I'll throw up on Canvas, that talked about the 2016 election. And in the 2016 election, Clinton was going up against Trump, and like every poll had Clinton winning popular vote, right? We'll just think about the popular vote. Electoral votes a little bit different, but in terms of the popular vote, they were all kind of predicting that Clinton was going to win it by quite a bit. And I believe she actually did end up having the popular vote advantage. It was very slight, but nonetheless, these polls were very far off from what the actual outcome was, right? They didn't predict that she was going to have like 1% more of the popular vote. They were predicting as high as like, almost double digits, right? So how did they get this wrong? So we can just think through some of the biases that could exist when it comes to political polling data, right? So maybe there's a selection bias. So if there was a selection bias, right, in all these polls that were predicting that Clinton was going to have this huge popular vote of landslide win, maybe we were somehow over-selecting Democrats, right? Maybe somehow we were doing, maybe you think about this as more of these polling centers might have been in larger kind of cities. Larger cities tend to be a little bit more kind of leaning towards the left than the right. And so maybe that was part of it, right? Maybe they weren't completely randomly sampling from across the country, right? They were randomly sampling kind of smaller subset areas of larger cities that were more likely to lean left. Now, I don't think that was probably what was driving it, but that's a possible selection bias that could exist. Another selection bias that exists is just that it tends to be these lists of people. Like if you ever, I did this when I was in college, like one of the candidates was like a call, make calls or whatever, and kind of would go door to door, even sometimes for local politicians. And so maybe the people that end up on these lists, like you can see that are registered voters, I think maybe it's because they put their name out there, right? So we get that more educated individuals are more likely to kind of be involved in these political events, more likely to be on the political party list. And the more educated individuals tend to, compared to less educated individuals on average, vote more towards the left as well. Now, not everybody, right? We're talking about just averages here. And so maybe I had somewhat of a selection bias there if I'm relying on these lists to kind of build these political polls, right? Now, I don't think there was this article and they talk about it. They don't think that's a huge part of it, because a lot of these polling places now, a lot of them are doing some of this online, right? So it's as long as someone has internet access, I'm kind of equally being able to reach out to across the country. But what's probably more likely did exist was this non-response bias. So why might have this influenced the results? So you can think about, if you go back at the time, Trump is a somewhat polarizing figure. And potentially people who knew they were going to vote for Trump were asked this question. Maybe there was a social cost to kind of saying they were going to vote for Trump, and they may just have not responded to these surveys, right? Like, I know who I'm going to vote for, but I'm not responding to this survey because I don't want to incur the social costs associated with saying that I'm going to vote for Trump in the election, right? So possibly we had more of these Trump voters staying quiet, what this article kind of called it, right? So we might have this non-response bias. Hopefully, we actually prefer them to just not respond. And the article goes into what they believe it was kind of the more the largest bias that existed, which was that where are we at? Malicious line, there we go. That these people who knew they were going to go for Trump, but didn't want to say so in a poll, would just say that they were going to go for Clinton, or say that they were undecided. When in actuality, they knew they were going to vote for Trump, but didn't want to incur the social cost, but they still also didn't want to not respond to the survey. So we'd rather have them not respond than maliciously lie and give us the exact opposite data, right? And so there was probably a little bit of both going on, where we didn't have as many Trump voters likely to even respond to our polls. And the ones that did, we might have had some of them maliciously lying, not wanting to incur a social cost of saying they're going to vote for a certain candidate. And then we might have had people unintended lying. This is just, undecided voters. We're doing these polls months before the election. And of course, something always comes out like a couple weeks before the election for both candidates. And so we might have had people who just changed their mind, right? Or non-malicious lying. But really, this is anything where we're looking at polling data. We can think about the bias that might exist, selection, non-response, and then think about how people might misreport, right? Malicious or non-malicious lie. Questions to this point? So just kind of an interesting way we start thinking about this data. We talked about then, all right, let's say we've done the best we can to eliminate that bias, right? Kind of a review of what we did last class. We'll do another example. And I have one thing I'll show you. So let's say we go back to that birth data, right? And I'm now looking at a sample, right? I've tried to eliminate all the biases possible. Luckily for me, this was hospital recorded data, so I don't have to worry about parental survey data where they're saying this is how much my child weighed, et cetera, et cetera. This is the actual recorded data from the hospital. So I'm pretty sure I've cut down a lot of the bias that exists. I look at this and say, okay, I know that birth weight, this random variable X, is normally distributed with a mean of what? 39 and a variance of 9. Right? I then take a sample of 81 infants, and I want to know what's the probability that the sample mean I see is below 80, above 39.5. Right? So the thing about here, the mean of my sample means should always be whatever that population mean was from the data I was sampling from. Well, here we know this is 39. I then want to know, okay, what's the probability I see a sample mean of 39.5 or anything greater? So right away, I know this probability has to be less than what? Yeah, right? The area to the right of the mean is 0.5. I want something a little bit less than that. From there, I need a couple more things, which is what's the standard deviation of my sample means? So remember, we said that the variance would simply be the original variance of the data we sampled from over our sample size. We wanted this standard deviation, so we then had to take the square root. So, right, if you square this, right, we had our variance for our sample mean was just the variance of the data we sampled from over our sample size. So this would be what? Square root of 9 over 81. So that's what, 1/9. So 1/3. Right. So we've got our standard deviation. We have our mean for the statistic we're now interested in, which is that sample mean. From here, and you could always kind of do this with the visual if it helps, kind of stack these normal distributions. So the normal distribution, you start out with the data itself, then the sample mean distribution, and then we want to take that sample mean normal distribution and turn it into a standard normal distribution. So how do we do that? We said we'll take that cutoff value for our sample mean, subtract the mean of our sample means. Well, that's just whatever the true population mean is. And then we divide by the standard deviation of our sample means, which we have this equation for, right? Now from here, just a matter of getting that cutoff value of 39.5, subtracting the mean of 39. And we actually already know what this is. This is where kind of breaking it down in steps might help prevent making some order of operations errors. I already calculated this up here. So instead of plugging the numbers in again, I could just say divided by 1/3, right? Or I could have actually written in the square root of 9 over 81 down here as well. Like I said, I always like doing it this way. It lets me visually think about this, as well as it just has, I have one number to plug into that denominator. Just as a reminder, I'll get out of the way here in a second. Right, that's really how we're finding that Z value, right? It's just that we know what the mean of the standard deviation of our sample means is going to be, right? So before I kind of go to my calculator even, just to kind of prevent myself from making like really extreme mistakes, if I'm about 0.5, right, 39.5 is 0.5 away from that mean, and the standard deviation is 1/3, I'm somewhere between 1 and 2 standard deviations, right? 1/2 would be, you know, if I'm thinking about the standard deviation as 1/3, it'd be more than 1, but not quite 2 standard deviations. Right? Now, if I actually plug this in, I think it should be exactly 1.5, right? And so if I get this z value of exactly 1.5, and I'm then interested in what's the probability I saw something that was as many standard deviations away from that mean as I did, right? 1.5 standard deviations away, or anything even further. So, cool. I was working on taxes. You guys don't need to see that. So, let's see, I got 1.5 here. It's my z value. So 1.50, right? That second decimal 0.9332, right? But what I have to remember is when I looked at z value from the table always gives me the cumulative probability, right? Or the probability of seeing something that many standard deviations away or anything less, right? So I've got the area to the left. I want the area to the right. The only thing I should have to do is, subtract that from 1, right? So 1 minus 0.9332 is what? 0.0668. So once we get to that z value, it's the exact same process as what we've been doing, right? It's just that to get that z value, turn that cutoff value we're interested in for the sample mean into a number of standard deviations away or into a z-score. Equation looks a little bit more complicated, right? It has a couple more moving parts. But the fundamental kind of construction of that z value is still the same. You subtract the mean of the statistic you're interested in from that statistic, and then you divide by the standard deviation of that statistic. Any questions on that before I keep going here? Okay. All right, so, and I added some of these slides in, so these I will upload these after class. So we went through this on the board. All right, we did kind of all this work. Just to make a point here. If I instead, let's say I found the exact same sample mean. So I'm interested in that cutoff value of 39.5, but I take a sample of 150 people, right? Or I take a larger sample. Okay? What's that going to do to the standard deviation of my sample means? Well, if the denominator is getting larger, it's going to drive down that standard deviation, right? Well, that's good for us because that means we're getting a more peak distribution, and that means it's going to be more likely that we see values around the mean. So now seeing something that's, 0.5 away, it's going to be even less likely, right? Because that same distance of 0.5, when I've got a smaller standard deviation, that's going to decrease my denominator, my z-score. It's going to drive up my z-score, pushing this out, maybe it's something like 3. Now the probability of seeing something 3 standard deviations away or higher is even smaller, right? So the idea is I could see the exact same cutoff value for my sample mean. It'd still be 0.5 away from that true population mean. But being 0.5 away, when my standard deviation is smaller, is going to be a higher number of standard deviations away, reducing that probability or that area to the right now. Okay. So anytime we take these higher sample sizes, it's going to be, less likely I see these values that are not equal to that population mean, right? Even if they're pretty close, right? 0.5 is pretty close, but if I take a sample size of 150, standard deviation is going to be small. If my standard deviation was 0.1, well, maybe I get to the, even being 0.5 away, well, that'd be 5 standard deviations away. Right? So these higher sample sizes, we can rule out these values that are kind of further from the mean a little bit easier. Or said differently, reduce the probability we see those values further from the mean. Because remember, in practice, we're only getting one sample. So we want to guarantee that that sample mean is going to be really close to that true population mean. All right. We'll do this. those should set us up pretty well when we come back from break. So we had I kind of went through a little bit last class, but a unique case of our sample mean we said was the sample proportion. So if we had this 1, 0 variable, I think the example I used last class was like maternal smoking, 1 if they smoked while pregnant, 0 if not. But this could be anything, right? This could be are they registered Republican or registered Democrat, et cetera. Just 1s if they are, 0 if not. We'll actually have to go back to thinking about this binomial distribution, right? So we can still calculate, it's still calculated the same way as a sample mean. It's just that our X variable is just 1s and 0s. So our numerator will always just represent the number of people who are 1s for whatever the situation is. Number of people who smoke while pregnant, number of people who are registered Democrat, number of people who have blue eyes, whatever it is. Okay? So we've got our sample proportion. Well, just like we had the mean and we had a standard deviation for that sample mean, well, we also know if I take enough samples, I come up with like 1,000 different sample proportions, we can do a nice frequency distribution. Those sample proportions will have their own mean. So what is the mean of these sample proportions? What ends up being just whatever that true population proportion is, right? Think about if I flip a coin, I know that if I were to do an infinite number of coin flips, the probability of heads is going to be 0.5, right? So my mean of my sample proportions, it'll just be centered around whatever that true population proportion is, right? And then my standard deviation for these sample proportions, well, if we go back to the binomial, you know, we kind of had there the mean for the number of successes with n times p. Well, here we're not interested in the number of successes, we're interested in the proportion of successes, right? So if I know that n times p will give me the number of successes, and I divide that by the number of possible outcomes n, and we cancel, I'd be left with just that population proportion. Similar idea, if I know the variance for my binomial is n times p times 1 minus p, right? And this is my kind of variance, right? My population variance. And when I'm thinking about, well, what's the variance? This is the variance in the number of successes. If I want the variance in the proportion of successes, divide by n, I get that variance on my variable should be p times 1 minus p. Remember what we were doing when we had, well, I'll do this one first. Remember when we were looking at the sample mean, we said the variance of our sample means is just the original variance of the data we're sampling from divided by our sample size. Well, here it's the same exact setup. It's just that I'm not looking at a sample mean, I'm looking at a unique case, which is the sample proportion. I know that the sample proportion should have a variance which is equal to p times 1 minus p. And then I'm looking at a sample statistic, so that's going to be the original variance divided by my sample size. Right? So it's very similar to my sample mean. It's just that for my sample mean, I had this known population variance. And for my sample proportion, I'll know what that population variance is. It should just be p times 1 minus p, according to what we were doing with that binomial distribution. So, and if we go down here, basically we take what we have before, dividing by n. So I've got my mean of my sample proportions is just whatever the population proportion is. And I've got that the variance of my sample proportions is p times 1 minus p, representing the population variance for a proportion, and then divided by n, just like we did with our sample means. And now from here, we know the mean, we know the variance. If we can get a sample size over 30, we're going to have a normally distributed, we're going to have a normal distribution when it comes to our sample proportions. They'll be centered around whatever that true population proportion is, and then have that variance, right? Well, now I've got a normal distribution. I can start to think about, okay, if I randomly sample 50 people, what's the probability that more than, I don't know, a portion of them that smoke while pregnant is 0.19 or whatever, and whatever cutoff we're interested in. So we'll go through an example here. Actually, I need to build out one more thing. Forgot. So before we get to an example, I might then be interested in certain cutoff values for that sample proportion. Maybe I want to know what's the probability I see that sample proportion or anything higher. Well, I should be able to kind of turn it into a z-score. So keep this up on the slides here. Right? I just want to make the connection to what we were doing before. It's very similar when we wanted to turn a sample mean cutoff value into z-score. So we had sample means. I'm going to write this out to hopefully, I think this will make a little more sense. Which, the fact that you showed up, this won't be in the recording, so this is an advantage, right? This is really what we want, right? We want to turn the statistic we're interested in, whether it's a sample mean or the unique case, which is a sample proportion, the mean of a 1-0 variable. We want to turn these statistics into z-values or into the number of standard deviations those are away from the mean of that population statistic. So we'll subtract the mean of our sample means, subtract the mean of our sample proportions, and then divide by standard deviation, or whatever statistic we're looking at. The only difference is, so for our sample mean, that standard deviation was the square root of the original population variance over our sample size. For our sample proportion, that standard deviation, well, we've got that right here on the screen, right? Should just be the square root of p times 1 minus p over the sample size. Okay? So we're doing the same thing. It's just that the variance is going to be a little bit different for a proportion as opposed to kind of just any normally distributed variable. Okay. Questions on this before you take on? Okay, so we've got our z-value equation now. All right, we could think about something like as simple as this. So let's say I've got a coin. And I know the probability that it comes up heads is 0.5, right? It's a fair coin. So if I'm thinking about the distribution of my sample proportions, I know that it should be centered around whatever that true population proportion is, which for a coin flip example is easy. It's like 0.5, right? So it'll be a little bit more difficult when we get away from these kind of easy examples like flipping a coin. But for the sake of starting out, right, we have that known population proportion. I then say, okay, what's the likelihood that I see 55 or more coin flips come up heads? So that would be 55 out of 100. I'm not always directly given what that sample proportion cutoff value is, but really it's just the number of successes divided by the total number of observations, right? So if here I want 55 out of 100, 55 divided by 100 would be that sample proportion of 0.55. Right? Our sample proportion is always somewhere between 0 and 1, but we're not always directly given it. Sometimes we have to kind of calculate. From there, I need to turn this into a z-value. So how many standard deviations away from that mean, right, or that true population proportion, is this cutoff value of 0.55? Well, got my z-score equation up here. So my cutoff value I'm interested in is 0.55. My, not 0.05. My population proportion was 0.5. Divide that by the square root of. Now, notice here, what's in our denominator? The variance, the original population variance will be based off of the original population proportion. So we're going to the denominator. It's not p hat down here, right? P hat is this cutoff value we're interested in for our sample proportion. P is going to be what the actual population proportion is. So here we would use 0.5. What? I said we're flipping the coin 100 times, so my n is 100. Now it's just a matter of getting this entered in my calculator, right? If I do that, it shows nice numbers apparently. So that we get this nice, easy z-value of 1, right? Being 0.5 away, or sorry, 0.05 away was 1 standard deviation, right? This is where if I had maybe done the kind of intermediate work and I calculated what was in this denominator just to get one number to plug in there, it was 0.05. Well, this would be an easy one to say, well, okay, if my standard deviation is 0.05 and I'm 0.05 away from that true population portion, I am 1 standard deviation away. Now, to kind of complete this out, we would go to our z-table, 1.00, 0.8413. So 0.8413, remember, is always the area to the left. We want the area to the right, so 1 minus that. questions on this one? Let me think. I'm not gonna use the iClicker. So these are just coin flip example ones. I'll leave you with one more thing. We'll do one more thing on the board here. So let's say what would be a good example to do? So let's say I know that in the population as a whole, there's something like, it's kind of a dumb example, but this is something that you could do with proportions. So it's something like a certain percent of people carry, I heard this recently, like 30% of the country or something can't cover a $500 unexpected expense or something like that. So let's say, what's the probability that, you know, I'm selecting a certain number of people, what's the probability that they can't cover this additional $500 expense, right? Household expense. Well, I know the population proportion is 0.3. I know 30% of people can't. And so if I were able to get everyone, right, I would know that, you know, I see this population proportion of 0.3. So if I'm thinking about my sample proportions, it should be that they're centered around that value, right? And on top of that, I could actually calculate the standard deviation of those sample proportions. And go back here. So we have, oh, there we go, right? Which is just the square root of that population proportion times 1 minus that. And let's say I'm interested, okay, what's the likelihood that if I look at, we'll do 50 people, right, that I see 40% or more of them can't cover this additional $500 expense, right? Well, I know that now I've got my sample size is 50, right? So I can go ahead and calculate kind of what that standard deviation is. I'll do it in Excel unless anyone else beats me to it. So we'll do what? The square root of 0.3 times 1 minus 0.3 divided by 50. So 0.064, right? So my standard deviation is about 0.06. So if I'm looking at this, when I turn this into a z-value, what's that z-value going to be pretty close to? Even if I don't have the equation in front of me or I can't remember it, if I just remember what the principle of a z-value is, what could I say that that z-value is in between? Close, right? So if how far away am I from that mean? 0.1. If my standard deviation is 0.06, I'm more than one standard deviation away. But am I 2 standard deviations away? Well, 2 standard deviations would be about 0.12. I'm not quite 2 standard deviations. I'm somewhere in between, right? So this is where calculating that standard deviation for the statistic you're interested in can just kind of help you envision, like, I'm not going to be able to get this perfect, but like I can look, oh, 0.1. Oh yeah, it's more than 1 standard deviation, not quite 2, right? Well, from there, I can't do that math in my head. So it's just a matter of kind of using that equation that we have for calculating that z-value, right? Now it's just a matter of plugging everything in, right? So 0.4 was that cutoff value I was interested in. 0.3, that was the population proportion. And then we know this denominator, once again, we don't have to plug everything back in because we already calculated it, right? All that denominator represents is the standard deviation, not of a sample mean, the standard deviation of a sample proportion, right? Well, we already calculated that. So now it's just a matter of plugging in here, 0.064, right? I don't know what this ends up being, but it's somewhere between 1 and 2. We can kind of prove this to ourselves here. So what? 0.4 minus 0.3 divided by 0.06. It's about 1.56, right? Once I have that, hopefully at this point, it's starting to get redundant. We know that, okay, I looked this value up in the table. Table gave me the area to the left. I wanted the area to the right. So I just subtract that from 1. Questions on this before we keep going here? All right, so I think I'll end it there. Like I said, hopefully this is kind of a good setup for us. We'll start doing confidence intervals on Monday when we come back from break. You'll probably see me throw up one of those smart books if you just want to take a look at it that week once we come back. They'll just be there for additional practice. Other than that, have a fun, safe spring break, and I'll see you guys next Monday.